Thank you, Doug, for sure.
Thanks, Kevin. Thanks, guys. Yep.
Meter is 6 times 10 to the minus.
Why did I ask that?
10 to the minus 3 meters, right?
Yes. Yep. Mhm. See you guys. See you tomorrow.
See ya. I forgot I had a. I have to do that. I wanted to do some BTS stuff tonight and then start my midterm. Oh, so I'm around the house.
Oh,
No, wait, no one was sitting there.
yeah. Maybe it's left from before. Just leave it there. I think they'll come back to it. I remember in college, I sometimes I would leave my sweater in the lecture halls,
Yeah.
and I wouldn't realize until 2 days later when I came back to the lecture. They said, "Hey, that sweater looks like mine."
Yeah.
Like, oh wait, that is my sweater. I left it here for 2 days.
I'll put it in.
Yeah. I guess no one's gonna pick up a stinky sweater from a random lecture hall too.
Yeah, true. I did take one thing in college and it was a water bottle that had been sitting at the front of the class, like I'm talking about for literally like 4 weeks.
Oh wow.
And I would see it like every time. And then finally one time I realized, I was like, damn, that's an expensive water bottle. I'm gonna keep that for myself. I went and took it.
Nice.
I was like,
Well,
all right, your grace period has expired.
yeah, they had a month to
I
pick it
will
up.
now be taking it. So on the midterm, is it strong form, weak form, 1D finite elements, and then Gauss quadrature?
Mostly, yes.
Okay,
Yeah.
all right.
Yeah.
And we have a Gauss quadrature. All right, I'm gonna try to be at your office hours tomorrow.
Okay. Yeah, I gave out one homework today. I had to change my plans a little bit because that homework actually has some more 2D stuff. But we're not deep enough into the 2D stuff for me to assign too much of it. And so it's a fairly short homework assignment, but I wanted you guys to get some practice with Gauss quadrature before the
The
midterm.
midterm?
Yeah.
I haven't even started it yet, and I need to finish this assignment tonight.
It's the homework's gonna be due on Monday, but
Okay.
it's fairly short. I think if you really concentrate, you can probably knock it out in an hour or something.
All right, yeah, because like, but I just hate when I come to your Thursday office hour, because like, that's the one that, like, because the other two don't fit well into my schedule this semester, which is why I haven't been coming as much. Because Thursday is the only one that really fits well, and I hate it when I get started on the homework, I ask you a couple questions, and then I keep going, and I realize like, oh man, I have more questions. So. oh, well.
You can always email me. You know, we can always chat on email too.
Okay, that's cool. All right, I'll do my best to make it work.
Yep.
Show.
You just messed up my whole birthday.
What happened?
It's on Tuesday. We have midterm Wednesday. We have that Wednesday.
Oh.
Just gonna have to wait till next weekend.
Yeah, it'll be better next weekend then. You don't have to worry about a midterm.
Not on Tuesday, you know, we give a shit. It's like after you're 30, doesn't matter. When you turn 31, it's like, no one gives a fuck. Or next big birthday is 40. That's good. Yeah, but yeah, it's on Wednesday. This Wednesday? Yeah. No, I'm just kidding. See what that would be? Never mind, I thought it would say that. It's in like 9 days. Yeah, that's- Yeah, I was like, shoot. Oh, man. Such a simple thing. We don't know what's gonna be on there, Dr. Tran.
Wait, what?
We didn't go over what's gonna be on there.
Yeah, so I'm gonna put out a study guide by Wednesday, probably by tomorrow. I'm gonna put out a study guide. But it's basically all the 1D finite element stuff plus Gauss quadrature.
Okay.
Yeah. All right, it's 7 o'clock, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Okay. It's stressful. I know it's week 13, man. Like we're almost at the end, and this is when things get really crazy. But yeah, hang in there. Summer's almost there, so you know, just a little bit more to go. Wednesday is 420, and so that'll be fun. And so you know, I can't partake because I'm working, but you know, be safe. You know, that's the only thing I say. My friends are all they're gonna watch 21 Jump Street together, and yeah, and I should say play along with the movie. I'll say that. So I think it's very appropriate. So that'll be fun. But wait, say again.
It's legal now. We don't have to use it.
That's true. That's true. Yeah, they're gonna get super high, super lit on that stuff. But yeah, it's funny because I teach 2 other classes on Monday, Wednesday, and they were supposed to have a midterm this Wednesday, but I pushed it back to Monday. And so you know, you can kind of you can kind of see why. I mean, for this class, you know, the plan was always to have a midterm next Wednesday, but you know, I didn't realize at the beginning of the semester that you know our Wednesday landed on 420, and so you know, so they asked to push it back, and I said, okay, you know, you guys have fun, just be safe and show up for the midterm on Monday. That's the only thing. Okay. So our plan for today is we're going to continue on with our lecture notes on 2D finite elements, right? And so, we got some good progress last time. And so today we'll actually get into the mechanics of how to actually compute some element stiffness matrices. And so that'll be fun. Okay. Some announcements I want to make is that, first of all, our midterm 2 is going to be next Wednesday. Okay, that's going to be April 27th. And so, what's primarily going to be on the midterm is going to be all the 1D stuff. And so strong forms, weak forms, finite element forms, and Gauss quadrature. And so that's what you can kind of expect. I might have a conceptual question or two just on the 2D stuff, but no calculations on 2D stuff. And so I'll put out an official study guide by tomorrow, just so that you'll know what to say. So exact same format as the first exam. And so we're going to take it in person. You can have a sheet of notes, 8.5 by 11 both sides. And besides that, it's closed everything else. Okay? I did want to give you one homework assignment on Gauss quadrature, and so I created a homework assignment today. It's very fast, and so it should be very, very fast. And so I know a week's not a lot of time, but I basically just want to give you just a little bit of practice with Gauss quadrature, just because we've only just been talking about it in the lecture, but I want you to try it on your own. So that's going to be due next Monday, just so that you have some practice with that before the midterm on Wednesday. Okay. Okay, and so that's it for my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and pick up where we left off. And so what we have here is 2D heat conduction. Okay. And we're learning how to do this with finite elements, 2D finite elements, but we're starting with the triangular element. Okay. And so this is with the 2D, or with a 3-node triangle. Okay. And so we were kind of in the middle of getting our expressions here. Okay. And so just to start us off, let's kind of just take a step back and remind ourselves the process that we go through to derive our element stiffness matrix. And so to derive an FEM element stiffness matrix, and this goes for any dimension. Okay, so this goes for 1D, 2D, 3D, any of the above. Okay. And so first we start with the strong form of the equation. Okay. Okay. And so we start with the strong form of the boundary value problem. And so that not only includes the governing differential equation, but that also includes the domain, as well as the boundary conditions and all that stuff. Okay. From that strong form, we get the weak form. Okay, and so that's primarily what we did last time. And so we took the strong form of the heat equation, we multiplied it by our weighting functions, we perform integration by parts, and we got our weak form. Okay. Then what we do is we apply that weak form on a finite element. Okay. And what that usually entails is plugging in expressions, plugging in assumed expressions for the weighting function and the solution function. Okay. So remember, our weighting function is given by W of X and Y, and our solution function is T of X and Y. Okay. And so for the 3-node triangle, we're going to have a three-term expression for each of these. Okay. Okay, so for W, X, and Y, what we have is W1 and 1 of X and Y plus W2 and 2 of X and Y plus W3 and 3 of X and Y. Okay. right? Where N1, N2, N3, those are our elemental shape functions or element interpolation function, right? Whatever you want to call it. And then we have a similar expression for T. And so T here we have T1, N1 of X and Y plus T2, N2 of X and Y plus T3, N3 of X and Y. Okay. Where in this expression for T, because it's our solution function, the T1, T2, T3 take on special, more special meanings. Okay. And for W, we have the W1, W2, W3, but we don't really care all too much for those. Okay. But what we really care about are these ones. Okay. And so T1, T2, T3, remember these represent the nodal solutions at the nodes of our element. Okay. Okay. And so visually it looks something like this. And so if we have a 3-node triangle like this, okay, very arbitrary shape. This is a node 1, node 2, node 3. Okay. And so our temperature solution at each of these nodes will be T1, T2, and T3. Okay. And I think last time we got up to the point where we got our expressions for the shape functions. Okay. And so just for the sake of completeness, let me go ahead and write them down. Okay. And so if we go through the process, and so remember the way that we compute these shape functions is that we first take an arbitrary function of X and Y, linear function, and then we require that solution to match the nodal solution values. Okay. And so if we do that, we end up with the following kind of gnarly expressions here. And so we have 1 over 2a times x2 y3 minus x3 y2 plus y2 minus y3 x plus x3 minus x2 y. Okay, so that's n1. Right. Obviously a lot more complex than our 1D cases. Okay. Then n2, n2 is 1 over 2a times x3 y1 minus x1 y3 plus y3 minus y1 x plus x1 minus x3 y. Okay. And then n3 is 1 over 2a x1 y2 minus x2 y1 plus y1 minus y2 x plus x2 minus x1 y. Okay. All right. And so, of course, getting these expressions, it's a very long, tedious process. It's a exercise in patience and determination and all those other strong words. But this is kind of what you get. All right, and so we kind of stopped just about here. And so, from here, what we're going to do is we're going to take these expressions for the shape functions and actually use them to compute our element stiffness matrix. Okay, so again, it's going to be a lot of writing, a lot of math. But the reason I kind of went over this whole process with you is to kind of remind you kind of where we're going. Okay, because the thing is with once you kind of get past 1D and even 1D to an extent, like we've talked about a lot in this class. Finite elements was not designed to be something that you work out by hand. Right? These are designed to be computer algorithms, and so it's just by its nature, it's going to be really tedious and really time consuming. But as part of this class, it's important to understand that process. So I want you to kind of, be aware of the process and kind of understand what we're doing, but not necessarily having to worry about all the tiny little details of everything that we're, that we're covering. Okay. Any questions on this? Okay. All right, and so the next step is we're going to take these shape functions and apply it to our weak form. Okay. But if you recall from our weak form, and you can recall this from our 1D case as well, part of that is also going to include the shape function derivatives. Okay. Because if you look back in your notes at the weak form, we have, specifically our element stiffness matrix term. We have a gradient of W dot product with gradient of T. Okay, and so remember, gradient of W, gradient of T. That means we're going to need both the X and the Y derivatives of W and T. Okay. Right, and so the way that we're constructing our W and T functions, when we take the derivatives of this, all that means is that we're taking derivatives of our shape functions. And so, let's write out what our shape function derivatives are for each of these. Okay. And so we're gonna have 6 of them. And so we have 3 shape functions, and we have derivatives in 2 directions. So we have X and Y derivatives for 3 shape functions. So that's going to be six expressions in total. Okay. All right, so there's no better way to do this than to start at the top. So we have partial n1, partial x. Okay. And we're taking the derivative of n1 with respect to x. What we get is y2 minus y3 divided by 2 times the area. Okay. Oh, if I haven't mentioned it, the area represents just the area of the triangle. Okay. Okay. Thankfully, when you take the derivatives, a lot of the terms go away because they're either constants or they don't depend on that variable. Next, we have partial n2 partial x. And so we have partial n2 partial x is going to be y3 minus y1 all divided by 2a. Okay. Then we have partial n3 partial x. So we take the derivative of the third shape function there with respect to x. Get y1 minus y2 divided by 2a. Okay. Those are all the x derivatives. And so now we're going to take the y derivatives. And so we have partial n1 partial y. Okay, partial n1 partial y is going to be x3 minus x2 divided by 2a. Okay. Then we have partial n2 partial y. Okay. Partial n2 partial y is going to be x1 minus x3 all divided by 2a. Okay. Then we have partial n3 partial y. And so from this, we get x2 minus x1 all divided by 2a. Okay. All right. And so we'll refer back to this. And so we'll do one example where we actually compute the element stiffness matrix, but it's good to be aware of what these values are. Okay. Okay. And so the next step is to actually compute our gradients. So let's start with the gradient of t. Okay. So remember, when you take the gradient of a scalar function like this, you end up with a vector, right? And so we're going to have one component, and I'll make this a column vector. One component is going to be partial t partial x, and the other component is going to be partial t partial y. Okay. And so if we apply that to our function t, which we defined up here, t1, n1, t2, n2, t3, n3, okay, then we get t1 partial n1 partial x plus t2 partial n2 partial x plus t3 partial n3 partial x. Okay. Then on the bottom row, we have t1 partial n1 partial y plus T2 partial N2 partial y plus T3 partial N3 partial y. Okay. And so that's our two element vector. Okay. But just for the ease of computing our element stiffness matrix later, I'm going to go ahead and put this in matrix form. Okay. Because what I notice here is that we have T1, T2, and T3 in both lines. Okay, so we can kind of separate them out and make it into like a vector matrix expression. Okay. And so another way that we can express this is the following. And so we can have first a kind of a flat vector or flat matrix. Okay. And so this will just contain all the shape function derivatives. And so we have partial n1 partial x, partial n2 partial x, partial n3 partial x. Okay. We have partial n1 partial y, partial n2 partial y, partial n3 partial y. Okay. And so this right here is a 2x3 vector or 2x3 matrix. Okay, so it has two rows. First row is for all the x derivatives, second row is for all the y derivatives, and the three columns there represent the three different shape functions, n1, n2, n3. Okay. And then we're going to multiply it by this following 3x1 vector. Okay, and so our 3x1 vector is just going to be T1, T2, and T3. Okay. Okay. And so we can say the gradient of T is equal to this kind of matrix vector multiplication. Okay. And so if you remember, in 1D, we did something very similar, except, in 1D it was a little bit simpler because we only had one dimension. Here we have, multiple dimensions. So these matrix expressions get a little bit more hairy, but still manageable. So does everyone kind of see how I got from kind of this first step right here, where I just computed the gradient, and how I separated it out into the matrix and vector? Does that kind of make sense to everybody? Any questions on this so far? Okay, all right, so that's gradient of T. But in our weak form, we not only need gradient of T, we also need gradient of W as well. Okay. The only difference here is that instead of putting it in that form, we're going to take the transpose of that. Okay. Okay. All right, and so if we take the transpose of the above expression, we have gradient of W is equal to W1, W2, W3. Okay. And then to that, we multiply by the following matrix. We have partial n1, partial x, partial n1, or partial n2, partial n2, partial x, partial n3, partial x. Okay. And then the second column, we have partial n1, partial y, partial n2, partial y, and partial n3, partial y. Okay. And so when you multiply these two vectors together, you end up with the same thing as up here, okay, at the very top of the screen. But I've just kind of mixed up the order. Okay, so I made it so that the W's come first and the shape function derivatives come second. All right. And so now that we have this, we're ready to plug into the weak form, which is gonna be a doozy. And so it's gonna be a lot of terms, because basically what you're gonna see is that we're gonna take this matrix, and we're essentially going to multiply by this matrix right here. So we have quite an intense matrix multiplication, and we're going to end up with the craziest 3x3 matrix you're going to see. Okay, and so there's no way around it, and so let's go ahead and do it. Okay. And so now that we have expressions for all of these, we're ready to plug it into the weak form. Okay, but I'm going to do it one integral at a time. Remember, our weak form is comprised of 3 different integrals, and so we have an integral with a balanced derivative, and so that's the gradient term. We have an integral that contains our Neumann boundary conditions, and we have an integral that contains our thermal generation function. Okay, so I'm going to do each 3 separately, and so let me start with the kind of the craziest one first. And so let's start with the balanced derivative integral. And so that integral is the following. And so we have a double integral over the area of gradient of W dot product with K gradient of T, okay, dA, okay, where K, remember, is our thermal conductivity, right? But you'll see it'll be very quickly be forgotten, because what we're going to do is we're going to plug in both expressions for gradient of T and gradient of W into here. Okay, and so if we do that, right, let me start with gradient of W. And so if we plug in gradient of W, we have W1, W2, W3. Okay, and so those are constants, and so I pulled them out. I pulled them out of the integral. Okay, and we have double integral over the area of partial n1, partial x, partial n2, partial x, partial n3, partial x, partial n2, partial n1, partial y, partial n2, partial y, partial n3, partial y. Okay. We have k. Okay. K will be the forgotten child. Okay. And then we have the shape function derivatives from gradient of t. So we have partial n1, partial x, partial n2, partial x, partial n3, partial x, right, partial n1, partial y, partial n2, partial y, partial n3, partial y. Okay. And then we're going to integrate this over dA. And then here we have our solution variables. So T1, T2, T3. Okay. Right, and now we have the fun part. And so you can see here, we have W1, W2, W3. We don't really care about that, but all the action is happening inside the integral. Okay? The good thing about this integral is that it's all of the shape function derivatives here are constants, and so we don't actually have to integrate anything, thank God. But we do have to perform this matrix vector multiplication. And so here we have a 3x2 matrix. We have a K, but the K is a constant, so or it doesn't have to be, but for all intents and purposes, we'll pretend it's a constant. And so we'll just have the K get out of the way. because we're going to multiply these two matrices together. So we have a 3 by 2 and a 2 by 3. And so they get married and they have a beautiful 3 by 3 child after that. And I will say beauty is in the eye of the beholder. And so feel free to call my child ugly. I won't feel insulted. Okay. So we'll pull K out. Okay. All right. And so let's go ahead and perform this multiplication. Okay. So let's do the top left entry first, because we know in the end we're going to get a 3 by 3. And so let's do the top left entry first. So the first row, first column. Okay. And so the way that we get that is we take this first row, right? And then we dot product with this first column, right? And so that's kind of how we do matrix multiplication. And so if we take the dot product of that, we have partial n1, partial x, partial n1, partial x multiplied by each other, plus partial n1, partial y, partial n1, partial y. And so that's just the top left expression. And so we have 8 more of these to go. Okay? And so this next one here is going to be partial n1. But after you do a few of them, you'll start to recognize the pattern. And so once you recognize the pattern, it becomes not as bad, although it is very tedious. And so that's the next row. Okay, actually, let me do this. That's the next entry. So the next entry after this, we have partial n1, partial x, partial n3, partial x, plus partial n1, partial y, partial n3, partial y. Okay. So let me separate like this. And so, normally you don't do these for matrices, but I think for this one, it's important to kind of keep track of, which terms belong to which columns. Okay. And so that's the first row of our matrix here. So we have, you can see in the top left, we have n1, n1. Then the next one, we have n1, n2. And the third column, we have n1, n3. Okay. And the pattern is that you multiply their x derivatives together, and then you add the product of their y derivatives together. Okay. So any questions on how we got this this row of the matrix here? Yes. Let me clean this up. It should be n3. All right, so that's the first row. Okay, I'm gonna go ahead and move on to the next one. I'm gonna go ahead and write out the next ones, but then we'll kind of zoom out just to kind of give everyone a chance to catch up. Okay. Okay, and so next row, instead of starting with n1, we're gonna start with n2. Okay, so we have partial n2, partial x, partial n1, partial x, plus partial n2, partial y, partial n1, partial y. Okay. Okay, so that's our second row. Okay. And so if you notice, in every pair, right? So we have basically, pairs of shape function derivatives multiplied by each other. The first of the pair represents the row of the matrix, and the second entry is the column, right? And so for the 2, 1 entry there, we have partial n2 partial x multiplied by partial n1 partial x. Okay. So that's kind of the pattern. So let me go ahead and write out the last row. So the last row we have partial n3 partial x partial n3, or excuse me, partial n1 partial x plus partial n3 partial y partial n1 partial y partial n3 partial x partial n2 partial x plus partial n3 partial y partial n2 partial y. And then we have 3, 3. And so partial n3 partial x partial y. All right, so that's our matrix. Okay. Okay. All right. So it's a monstrosity, right? And so it's it's a lot of terms. And so remember what I told you, this is not designed to be a hand calculation type of algorithm. Okay? But this matrix that we have right here, okay, this 3 by 3 matrix, this is basically our element stiffness matrix. It's there are a couple other things, and so of course you can't forget K. Okay, so our K is still out there, he's chilling, but he's gonna multiply the whole thing, and we also have to perform this integral as well, right? And so that integral is we can't forget that as well. But luckily, all these shape function derivatives for a linear triangle, they're all constants. Okay. And so when you perform the integral of a constant, you just get the area, right? And so this integral here just becomes the area, right? And so this shape function, this element stiffness matrix ends up being K times A multiplied by all of this stuff. Okay. All right. Any questions on this? Okay. Right, remember, you're not doing these by hand usually. You're writing computer algorithms to do it. So just kind of keep that in mind. Okay, so there's our element stiffness matrix. Okay. And so let's go ahead and write out the similar expressions for the 2 other terms that are weak form. Okay. Okay. And so first, let's do the Neumann boundary condition term. Okay. And so the Neumann boundary condition term is a line integral. Okay. Right. Don't worry, we don't have any more matrix multiplications, and so that's kind of as bad as it gets. Okay. And so for the Neumann boundary condition term, we have line integral over the boundary of an element. Okay, so we have partial A of W times heat flux ds. Okay. And so we plug in for W. We plug in for W, what we get is minus W1, W2, W3. Okay. Line integral of and 1, and 2, and 3. Okay. And all these are functions of x and y. ds, or q bar ds. Okay. And so this expression right here will make contributions to our element forcing vector. Okay. Unfortunately, this is a lot more difficult to integrate because we don't have shape function derivatives here. We have the shape function straight up, right? And so our shape functions are functions of x and y. And so this is something that you would actually have to integrate, or you can apply Gauss quadrature for that. Okay, but I'm not gonna submit you guys to that torturing. So we'll just leave that as is. But we'll kind of leave a note that this is kind of how you would do it. Okay. All right, so that's the Neumann boundary condition term. Right, we also have the thermal generation term as well. Okay. And that's also going to make contributions to our element forcing vector. Okay. And so with this, we have double integral over the area of the product of W of x and y times S of x and y, okay, dA. And so we plug in for W, and we only plug in for W. And so we end up with W1, W2, W3, okay, double integral over the area of N1, N2, N3. Okay. And all these are functions of x and y. Okay. We multiply by our thermal generation function, and we integrate over dA. Okay. All right, and so of course, what you would do from here is you would add both of them together, okay, and that would be your element forcing vector. Okay. And so in the end, right, once you kind of put all this together, and so you have your element stiffness matrix up here, you have your element forcing vectors down here, we have just a normal elemental system, right? And so we have KE. Okay, so KE, here's our element stiffness matrix. Okay. We multiply that by T, and so T is our solution vector. Okay, so that came from up here, right? And so, I forgot to put it here. So we have T1, T2, T3. Okay. And so as part of our element stiffness matrix computation, we have our solution vector right alongside it. Okay. And this is equal to Fe, where Fe is our element forcing vector. Okay. And so we have a regular old finite element system, okay? Just with a shit ton of math that goes into it, okay? All right, and so next I do have an example. And so, it's a lot of arithmetic, but just to show you, what you would do to actually compute the element stiffness matrix of a triangle. Okay. Okay, so before I get to that example, are there any questions on what we've done so far? Okay, all right, so let's go ahead and do an example. All right, so this example, let's consider the following triangle. Okay. And so we have a triangle that looks like this. Okay. And so this will be node 1, this will be node 2, this will be node 3. Okay. We also know the XY coordinates of these nodes. And so node 1 we'll assume is at the origin. And so that'll be at 0, 0. Node 2 here will be at 1, 2. And node 3 will be at 2, 1. Okay. So those are the X and Y coordinates for each of those nodes. Okay. All right. And so based on this element here, let's compute the element stiffness matrix for this triangle. Okay. Okay. All right. And so, thankfully, we only need the element stiffness matrix. And so, we don't need the shape functions themselves, but we do need the shape function derivatives. Okay. Okay. And then to compute the shape function derivatives, we have most of what we need. And so we have the X and Y coordinates for each of the nodes, right? But the other ingredient that we need in the shape function derivatives is the area of this element. Okay. And that's not immediately obvious, right? Because normally the way that you compute the area of a triangle is you do 1/2 base times height, right? At least for a right triangle, right? Now, but this doesn't look quite like a right triangle, and it's not, okay? And so we can't directly apply this formula. But luckily for us, there is another formula out there that lets you compute the area of the triangle based on the coordinates of its vertices. Okay. Okay. And so the other triangle area formula is A. And I need to write down here, A is equal to 1/2 times x1 times y2 minus y3, okay, plus x2 times y3 minus y1 plus x3 y1 minus y2. Okay. All right, and so we have all of those in the example, right? And so we have x1, x2, x3, y1, y2, y3. And so we plug in all the numbers for this, we get an area of 1.5. Okay. Meter square, centimeter square, millimeter squared. Who knows? Who knows what I was thinking 2 years ago? And so it could be anything. Okay. And so now that we have the area, we can go ahead and compute our shape function derivatives. Okay. All right, so let's start at the top. And so we have partial n1, partial x. And so this is y2 minus y3 divided by 2 times the area. Okay. If we go ahead and plug in our values for this, and so we have y2 is equal to 1, and y3, or excuse me, y2 is equal to 2, and y3 is equal to 1. Okay. We plug in the numbers for this, we get 1/3. All right, next we have partial n2 partial x. And so partial n2 partial x is y2 minus y1 divided by 2a. Okay. And so we compute that and we get 2/3. We have partial n3 partial x. And so this is y1 minus y2 divided by 2a. And so this is minus 2/3. Okay. All right, next we have partial n1 partial y. And so we have x3 minus x2 divided by 2a. And so this is 1/3. Okay, then we have partial n2 partial y. And so this is x1 minus x3 all divided by 2a. So this is a minus 2/3. And we have partial n3 partial y, which is x2 minus x1 divided by 2a. And this is a 1/3. Okay. All right. So we have the area. We have all 6 shape function derivatives. And so now all we need to do is just plug and chug, baby. Okay. Okay. And so I won't submit you to the torture of me writing just tons and tons of things again, right? But basically what we can do, so this would be my second time using this. Okay. So let me go ahead and take this expression here. Okay. We'll go ahead and move it down. Magic of technology. Technology is a wonderful thing. Okay. And so we have everything here, right? And so all we need to do is just plug everything in. And so just as an example, let's do the top left term. And so we have partial n1 partial x, partial n1 partial x. And so this is going to be 1/3 times 1/3. Okay. Plus partial n1 partial y squared. And so this is going to be 1/3, 1/3. Okay. And so we're going to do this, for basically all 9 terms. Okay. So, feel free. I think I have one problem like this on the homework. So feel free to use MATLAB for it, just so that you don't submit yourself to torture. Okay. Okay. And so after we do that, so after a shit ton of arithmetic, okay, we end up with the following. And so we end up with 2/9, 0, minus 1/9, 0, 8/9, minus 6/9, minus 1/9, minus 6/9, and 5/9. Okay. And so that's what you get from the raw kind of just plugging in the shape function derivatives into this expression. Okay. But we're not done yet. And so, remember the shape function or the element stiffness matrix isn't just comprised of these shape function derivatives. We also have to multiply by k, and we have to multiply by the area. Okay. And I think I forgot to give you the thermal conductivity, but let's assume, just to make the numbers really nice and pretty, let's assume that K is equal to 6 here, okay? And so we do K times A is going to be 6 times the area. We've already computed the area. So the area is 1.5 is equal to 9, okay? And so if we multiply 9 by this entire matrix, what we get is 2, 0, minus 1, 0, 8, -6, -1, -6, and 5. Okay. Right. And so that's kind of how you would compute the element stiffness matrix for this. Okay. And so I show you this example, not as something that you would do normally by hand, right? And so, even for this, you can see that we skipped a lot of the steps. But I wanted to walk you through the logic, right? And so normally, if you have an element like this, let's say for your project, right? You would write a for loop, or you would write the code to automate a lot of these steps for you, right? And so you would write code, let's say that you start by writing code to compute the area, right? And so you would plug this formula into your MATLAB code. So you say area is equal to this formula here. Okay. Next, you would write codes to compute the shape function derivatives. Okay. Using all these expressions here. Okay. Again, it's a lot of formulas, but if there's one thing that MATLAB does really well is that it automates these formula computations for you. Okay. And if you're really clever, what you would do is that you would write these shape function derivatives into vectors. Okay. Or I guess into matrices into code. Okay. And because if you encode the shape function derivatives as matrices at first, then all you have to do is just multiply them together in order to get the element stiffness matrix. Okay. And then once you get the element stiffness matrix, you can multiply by k, you can multiply by the area, and then you end up with this element stiffness matrix here. Okay. Right. And so, I wanted to show you the steps to doing this because, it kind of helps you in developing the code. Okay. And in fact, I don't have the solutions like it, right now. But technically, you could do the project using this exact method right here. Okay, so I know in the project I tell you to use isoparametric elements, which we'll go over, very soon, and so hopefully by later this week. But you don't have to do you don't have to do the isoparametric elements, and so you can actually use this method right here. So actually, if you want to implement a project using this algorithm, you're kind of equipped to do so, and so you can go ahead and start doing that right away. Okay, any questions? Any questions on this example here? Okay, so that's the 3-node triangle, right? And so, hopefully this is not too much bad news, but the 3-node triangle is probably the easiest element that we'll do in 2D. Okay? And so the next thing we're going to do is we're going to step up the complexity by 1. And so we're going to go over the 4-node rectangle. Okay. Okay, so the 4-node rectangle is exactly as it sounds. And so we have a rectangle here. That's 4 nodes. Okay, 1, 2, 3, 4. Okay. And so of course, each of these nodes are going to have their coordinates. So we have x1, y1, x2, y2, x3, y3, and x4, y4. Okay. And of course, they're all going to have their own nodal solution values as well. So we have T1, T2, T3, and T4. Okay. All right. And so we have a brand new element with an extra node, but we can follow the exact same process that we followed for our triangle. Okay. And so if you remember, what we start out with was a generic linear function. Okay. And so we have t of x and y is equal to a0. You got to have the constant term. We have one term in x, one term in y, right? So we have a0 plus a1x plus a2y. Okay. And so that's the generic, that's the assumed function that we use for the 3-node triangle, right? And it worked out for the triangle because you can see here we have 3 unknown coefficients and we had 3 nodes in the triangle. So it worked out really well. Okay. Unfortunately, we can't use the same function for the rectangle because we're missing one constant. Right? And so with 4 nodes in the rectangle, that means we're going to need to have 4 different terms. Okay. But we've run out of linear terms, right? And so linear implies that we just have the variable just kind of by itself, right? And so we have x by itself and y by itself. And so we don't really have any other options. And so we have to form, what I like to call like a pseudo-linear function. Okay. And so instead of going up to quadratic, and so instead of doing like x squared or y squared, we do the product of x and y, okay? And so there is our assumed function. Okay? And of course, the big elephant in the room is this mixed term. Okay, so we have xy here. And so technically this term is quadratic because we have the multiplication of 2 variables together. Okay. And so it's technically quadratic, but if you look at x individually or y individually, they are still linear. Okay. Okay. And so, what I like to call this term is that even though it's technically not a linear term, I call it pseudo-linear. And so it's linear in a lot of practical different ways. Okay. All right, so that's our 4-node rectangle. Okay. And so of course the next step is to solve for the constants a0, a1, a2, a3. Okay. And remember, the way that we do that is by requiring that our function here matches the nodal solutions. Okay. And so when we compute t of x1, y1, this should equal to t1. Okay. Similarly, if we do t of x2, y2, this should equal to t2. Okay. And t of x3, y3 should be t3, and t of x4, y4 equal to t. Okay. Okay, and so what we get in the end is a four equation, 4 unknown system, right? And it's all symbols. There's no numbers, and so MATLAB can't save you here. Maybe Wolfram Alpha can, but it's not a fun system to do. But in theory, this is kind of how you would solve. That's how you would solve the system. Okay, and so through that, you're going to get expressions for A0, A1, and A2. And A3. All right, any questions on any of this? Okay. All right, and so if we do that, We can, of course, rearrange the terms so that we express everything in terms of shape functions, okay? Okay, and so we can have t of xy is equal to t1 and 1 of x and y plus t2 and 2 of x and y plus t3 and 3 of x and y plus t4 and 4 of x and y. Okay. All right. And of course, the moment you've been waiting for, here are the shape functions for the four node rectangle. Okay. So you have n1 of x and y. This is equal to x minus x2 divided by x1 minus x2 multiplied by y minus y2 divided by y1 minus y2, okay? Then we have n2 of x and y is equal to x minus x1 divided by x2 minus x1. Then we have y minus y1 divided by y2 minus y1. Okay. Then we have n3 of x and y is equal to we have x minus x1 divided by x2 minus x1. Okay. Then we multiply by y minus y1, y2 minus y1. Okay. Then we have n4, x minus x2 divided by x1 minus x2. And then we have y minus y1 divided by y2 minus y1. Okay. Yeah.
Is node 2 and 3 the same?
Yeah, so that's a good observation. So I kind of messed this up a little bit up here. And so notice how there's no x3, y3, or x4, y4. And so what we're basically working on the assumption that these two, the two nodes on the sides, they're lined up with each other. And so we basically have a parallel side rectangle. And so the more accurate thing to do here would be that this is, the bottom left is still x1, y1. But instead, everything else will be a little bit different. And so this would be x2, y1. Okay. And so we assume that node 2 is kind of parallel in terms of the y coordinate with node 1. Right. Node 4 is right above it. And so this will be x2, y2. And then the top left node, this will be x1, y2. Okay. And so this isn't even the most arbitrary rectangle. And so this is kind of a very special case. And so we're going to assume that the size of the rectangle align with the x and y axis. Yeah, sorry about that. I should have mentioned that before. Okay, and so we have perfectly vertical sides of the rectangle and perfectly horizontal tops and bottoms. Okay, and so that's why we end up with this expression here. Okay. All right. Okay. Any questions on how we obtain these? Okay. All right, and so from here we can follow the exact same process we did for the triangle. And so the next step, of course, is that we want to take these shape functions and apply them to our weak form. Okay. And then, of course, to do that, we're going to need the gradients. And so we're going to need gradient of T and gradient of W. Okay. And so just like we did with the triangle, and so just like we did with the triangle, when we compute these gradients, that means we're going to need the shape function derivatives. Okay. So that means we're going to need partial n1 partial x, partial n2 partial x, partial n3 partial x, partial n4 partial x. Okay. And the same thing with y's. And so, it's just kind of the same process as the triangle, but now there's more of them. Okay. So now we have, instead of 6 shape function derivatives, we now have 8 of them. Okay. And then from here, it follows the same process. And so we take, gradient of t, we put it in matrix form. We take gradient of w, put it in matrix form. We multiply them by each other. Okay. Except the difference now is that, because we have 4 shape functions, that means our element stiffness matrix is going to grow again as well. Okay. And so now the element stiffness matrix is 4 by 4. And so, if you thought the triangle was bad, this is, the same thing, but with 1 more row, 1 more column. Okay. And so this one, I definitely, we're definitely not going to do this by hand because it would be torture. It would take 20 minutes just to write out the entire thing. Okay. But there's an added complication. Okay. And so there's one thing that actually makes this a lot worse than our triangle. It's a little bit hard to see when you're looking at the individual shape functions, but so let me go back to the original kind of interpolation function that we had, okay? Because that's enough to kind of illustrate the point. Okay. And so if we look at our original t of x and y for the rectangle, right? Look at the term that I've circled in pink right there, right? So we have a2 of x and y, or a3 x and y, excuse me. And so what's going to happen to this expression when we take, let's say, the x derivative, right? And so let me take this right here, and let me just compute, just as an example, partial t, partial x, okay? Right. I know it's not the same as the shape functions, but it should illustrate the right point. Okay, so we take the derivative here with respect to x, we end up with a1, which is good, right? Because that's one constant, just constant. But then we also get a3y, okay? And so that's a problem because this, right, this little fucker, he's not a constant anymore, right? Okay. Why is that a problem? Okay. When we plug this into the weak form, we're going to end up with something like this, right? And so we get a double integral of the gradient of w multiplied with k, gradient of t times dA, okay? But for this one, because we're in rectangular coordinates, we can say it's dx dy, okay? If you remember for the triangle, we actually didn't perform any integration, right? Like the actual, matrix multiplication, Yeah, that was a pain in the ass, but we didn't actually have to perform any integral. Okay. But now, if we actually write out the expressions for gradient of W, gradient of T, these guys are no longer constant. Okay. And so if those guys are no longer constant, that means we actually have to integrate. And every term in this expression is going to have a different powers of X and Y. Okay. Okay. Imagine doing 16 different integrals, all for the sake of just one element stiffness matrix, and then doing it again for the next element over, right? And so this is not something you could do. You can definitely not do this one by hand. Okay. And so that's a problem. And so technically you can do it, right? But remember, we have a trick to make integrating easier. Okay, and that trick is Gauss quadrature. Not that we would do this by hand, but it's a lot easier to code it with Gauss quadrature. Okay. Okay. And so we've already done the 1D Gauss quadrature. And so what we'll do on Wednesday is we'll see how we can adjust the Gauss quadrature procedure to account for 2D stuff. Okay. And what you'll see is that it's not that bad. It's more or less the same. Okay. We just have to apply it twice. But the thing that's going to be difficult is when we have to apply our change of variables. Okay. So that's going to be the big difference between 1D Gauss quadrature and 2D. Okay. But that's going to lead us. The 2D Gauss quadrature is going to lead us to kind of the core, I would say it's kind of the core theory of a lot of modern finite elements, which is isoparametric elements. Okay. Okay. And so I know today was a lot of writing and a lot of linear algebra. So thank you guys for sitting through it with me. But this is kind of it's all kind of necessary and kind of set up for kind of where we're going. So any final questions today before we wrap it up?
So for the midterm, we're only doing this for 1D, right?
Yes. Yeah, I might ask you a conceptual question for 2D stuff, but no computations at all.
Okay, so just similarly, like the example we had in the last week.
Exactly.
Okay.
Yeah.
Thanks.
Okay, if there's no more questions, let's go ahead and wrap it up here. So thank you everyone for tuning in today. Thank you everyone for being patient with me. I know today was a rough lecture, I know. But once hopefully you can start to see this all kind of come together. Especially now that the project's out there, you can kind of see this all kind of coming together for the project. Okay. Oh, someone in class asked a question if the 2D stuff was going to be on the midterm exam. And so I'm not going to ask you to calculate any element stiffness matrices in 2D. I might ask you a conceptual question on 2D stuff, but all the computations on the midterm exam will be on the 1D stuff. So strong form, weak form, finite element form. So exactly like homework 2, basically. Yeah. Yeah. So I will ask you to calculate 1D problems, but no calculations on 2D problems. Yes, and it's still 4/27. Yeah, next Wednesday. Okay. Yeah, thanks guys. Have a good evening. Yeah, I'm gonna put the study guide together tomorrow morning. Yeah. Yeah, I'll send it out, and I'll put a poll out there too, and I'll record the review video on Friday. Yeah, so just like the first midterm. Thanks, guys. Ryan, Timothy, Merriman, any final questions before I close up the Zoom call? Okay, great. All right. Good night.